Hi everybody. So here we go with lesson 3 on transformers. So we're going to change pace a little bit. First two lessons were really theory lessons, magnetism and induction. Now lessons 3 and next week's lesson 4 will be on applying that information. So we're going to talk about transformers today. Pete's going to talk about power generation next week, and generators and motors are another piece of equipment that uses magnetism and induction to create some kind of an electric tool or some kind of electrical equipment. So we're going to talk about transformers today. There are 3 parts to this. This is a really long PowerPoint. If you've had a chance to print out the slides ahead of time so you can follow along, you can see that there are lots of them. So I'm going to break the video up into 3 parts, part 1, part 2, and part 3. So this first one's going to be fairly lengthy. The other 2 might be quite a bit shorter, but combined as a single video, it would be huge. So let's get started with part 1. So transformers can be very small or absolutely massive. This picture here is a great big giant one, but they all do the same thing. Okay, they take and they change the voltage, and I put in there and current because you can't have one without the other. Okay, changing voltage, transforming voltage has the result of transforming the current also. Okay, typically the purpose is to change the voltage, and the current happens to be sort of a side effect, but it's not possible to do one without changing the other as well. So that's what a transformer does. Okay, they are everywhere within the electrical industry. Okay, so this picture shows a transformer in a substation distributing power. This is how we get power from the generating station to your home, hundreds, maybe even thousands of kilometers away. Okay. On the other hand, very small transformers can be used for lots of different electrical needs, even within your own house, such as operating a doorbell. So here's what a transformer looks like that might operate your doorbell. So very different in size, exactly the same in terms of the theory behind what it does and how it works. Okay, so transformers operate using electromagnetic induction, which was lesson 2 that Pete taught you. Because induction requires motion, transformers only work in AC circuits. So there's no moving parts in a transformer, right? You look at the big one in the previous picture, you look at the little one here, there are no moving parts. So where do we get that motion that's required for induction? That's the AC power supply. So because the current is constantly growing and shrinking and changing direction and growing and shrinking, the magnetic field is doing the same. It's expanding, it's collapsing, it's changing in polarity, it's expanding, it's collapsing, and that's where we get the motion. Okay, that's what causes the cutting action, the relative motion between the conductor and the magnetic field. It's because the magnetic field is moving. There are no moving parts to create that motion to get our induction. Okay. Gotta check my notes to make sure I've covered everything before I move on. Here's the final slide in the introduction. This is what a typical transformer looks like. We think about, when we talk about transformers, we sort of envision what we're looking at here, these 2 pictures. Let me get my pen. So here's the image of how it's built. Oh, sorry about that, that's ugly. And this is more the diagram image. So when I'm drawing pictures quickly, I will draw something that looks like that. And then we can have the conversation about what's going on. So this is what we envision when we talk about transformers. They don't have to look like this, okay? But typically that's what we think of. So what are we looking at here? We are looking at 2 separate coils of wire that are interacting with one another, okay? But they're said to be electrically isolated. They are absolutely 2 separate electrical circuits. They're not connected in any way, okay? But they are said to be magnetically coupled because it's the magnetic field that's interacting, that's causing these 2 coils to interact. It's through the magnetic field, okay? Now, in terms of labeling, you'll notice that this coil is referred to as the primary coil, and this coil is referred to as the secondary coil. So these are how we refer to our two coils, primary coil, secondary coil. We identify them based on the way the transformer has been connected. Okay, not constructed, but connected. All right, the primary coil and secondary coil are absolutely interchangeable. We can flip them back and forth. What causes one to be labeled as the primary is that is connected to the power supply. So the power supply connects to the primary coil. The AC power supply creates the expanding and collapsing magnetic field. It's that expanding and collapsing magnetic field that interacts with the secondary coil, cuts across the secondary coil, induces a voltage into the secondary coil, and so that secondary coil then becomes the power supply for the other circuit. And that other circuit is then what gets connected to the load. So the secondary coil is recognized as a secondary coil because it's what provides voltage and current to the load, whatever we connect to this transformer. Okay, so primary and secondary, those are two really big terms. We'll talk more about them when we get into the math, which comes in part 3 of this lesson. We're going to spend some time though talking about the construction. Okay, there's basic construction, but then there's also variations to it. Okay, so you can see the images here. We have itty bitty ones and great big large ones. So this is where we're going to spend some time talking. Many different types and styles, ranging from small air-cooled signal transformers up to very large liquid-cooled three-phase transformers. So cooling is part of the conversation we're going to get into as well. Transformers are not 100% efficient. Okay, there's not quite as much power comes out on the secondary as went in on the primary. Where does that power go? Well, it gets dissipated in the form of heat. Okay, and so dealing with that heat becomes part of the conversation about how we build a transformer. So we're going to look at that a little bit too. So again, all kinds of different variations. We have images here. We can see lots of different constructions. Different core material becomes part of the conversation. That one equation that Pete showed you talked about the permeability of the core within a coil, and that is part of the equation. That equation was to determine the inductance of an inductor. Okay, so the core material is definitely a relevant part of the conversation when talking about transformers. Okay, we have different terminal types. How do we actually connect to the transformer to get the power in and to get the power out? Okay, and these different designs depend on their purpose and their application, their size, all kinds of stuff. Okay, so here we go. This image, it's a different picture, but we can see that it looks very much like the picture that we've already looked at. Most common type of transformers have cores constructed from laminated sheets of steel. Okay, so why is it a steel core or an iron core? Well, because it's highly permeable, okay, which means that it can focus those lines of flux. Okay, the magnetic lines of flux want to travel through that highly permeable material, which means this particular core is going to transfer those lines of flux from the primary coil over to the secondary coil without very much leakage. Okay, so that leakage is a form of loss. That's a lack of efficiency in the transformer. Those are lines of flux that are just sort of wandering off into space and not influencing the secondary coil. Okay, so that's why we want an iron core, some kind of sheet of steel, something highly permeable. Second question is, why is it laminated? Well, the laminations minimize what we call eddy currents. Okay, eddy currents can be roughly defined as any unwanted current. Okay, this iron core, it will conduct electricity. So we have cutting action. We have lines of flux that are moving around, creating induced voltage. Okay, there's going to be induced voltage in the core itself, which is going to push current through the core itself. If it's a great big hunk of iron, you're going to have fairly large currents. But by laminating it, by cutting it into very thin slices, we really reduce that eddy current effect. And that's another loss that we're trying to minimize. Okay, I think the next slide gives us another picture to have more conversation about this. Okay, well, here's a picture of the laminations. So this is a real transformer, and we've zoomed in on the core material, and we can see that it's cut into these thin slices. Okay, so the iron core concentrates the magnetic lines of flux and reduces the flux leakage, enhancing the transformer. So that's the iron core part of it, and then the laminations. So here we are. We can see eddy currents. The top picture is just one big hunk of steel, and we can see currents going all the way around through the entire thing. When we slice it into smaller pieces, we still see those currents, but now they're much smaller. Okay, so we cannot eliminate the effect of eddy currents. We can't make it go away entirely. Okay, but by laminating it, by thinly slicing the core, we can minimize the effect, and that minimizes the heat generated by those eddy currents, and it maximizes the efficiency of the transformer. Okay, so now in terms of the actual shape of the core, we've got many different options. Okay, if we look at, so the columns here, we've got single phase and three phase. We're going to eliminate the three phase conversation for a minute. That's, I think, lesson 5, three phase. We get back to that. We're going to eliminate that for the time being. Let's focus on the single phase, and we see that we have a core type and a shell type. Okay, and in the core type, the primary and secondary coils are wound separately around parts of the core. Okay, in the shell type, what we do is we actually wrap the primary and secondary coils around each other, around a section of the core. Okay, let's look a little closer here. So first of all, the core type. And again, this is a picture that matches the images we've seen so far. So windings are placed around each end of the core material, primary winding on one side and the secondary on the other side. And it's the core material that transfers the lines of flux from one from one winding to the other. Okay, this is very typical. That's why all the images we've seen so far have looked like this, because it makes sense. Visually, it makes sense. Logically, it makes sense. It's all good. Everything's wonderful. However, the shell transformer actually offers a little bit better efficiency. Okay, and what we're doing here is we are winding the primary and secondary windings around each other, around the center bar of the transformer. And now, if we were to draw the lines of flux on here, they come up through there and around and back in there, and also around this way. Okay, and as they expand and contract, okay, as a result of the AC current through the primary winding, they're cutting through the coil of the secondary winding. Okay, it proves to be a little bit more efficient in terms of its construction. A little bit more expensive though. This is a larger core, so you've got a bigger transformer. You need more highly permeable iron to build the core. Okay, so I mean there are pros and cons, right? And so then the conversation always comes back to, what are your needs? Do you need something that's lighter and more transportable, or are you willing to go with something bulkier because it's more efficient? And there's always this trade-off. What is your needs specific for the transformer? Okay. Now we can move one step beyond the E-type shell. Oh, good. So here I was hoping this is the picture I was looking for. Good. So here's a comparison between our core type and our shell type, and we can see the lines of flux through the core material. Okay, the core type on the left, we see the lines of flux from the primary transferred to the secondary, and the shell type on the right, we can see the lines of flux going around through the outer bars of the core, but as they expand and contract, they cut through the secondary coil. Okay, good. But now I think the next slide takes that shell type and moves one step further. So the H-type shell is the very same, except now it's a three-dimensional version. Okay, so instead of just having a pair of outer shells, we now have 4, because remember we tend to draw everything on a piece of paper and we think about it and we learn about it and understand it two-dimensionally, but let's not lose sight of the fact that the cloud, which is the magnetic field, those lines of flux, they are spread out three-dimensionally. Okay, and so the H-type shell transformer addresses that. And so once again, what are your needs? Okay, obviously this is bulkier yet, more expensive in construction, but we just continue to increase our efficiency of the transformer. Okay. Here's another design. Okay, and this is very much like the shell type. Okay, except we've changed the shape. Okay, and I can't even say this word. I have stumbled over it for years. Toroidal core. It's and these are affectionately referred to in the industry as a donut, because that's exactly what shape it is. Okay, so we have a core now that is a round ring, and the coil is simply wrapped around it. Okay, and again, it comes down to functionality. These are typically very small, okay, and very specific purpose, which we'll get into a little bit. Okay, so the toroidal core typically gets used for higher frequencies, okay, tens of kilohertz to megahertz, reduced losses. It's a nice small package, so physical size is simplified and shrunk down. And the weight of the switch mode power supplies, all that stuff just means whatever your particular need is. Okay, they're typically used on power cords for appliances. So if you've ever noticed your power cord, particularly for your laptop, I bet you just at the end of it where you plug it into the wall, there's a larger space. I don't happen to have one right in front of me. I'd love to hold it up and show you. And it probably has a little toroidal transformer right there at the end of the power cord. But the final statement there on that slide says too expensive for use with larger distribution equipment. Now, we could also use an air core, so no core at all. Okay, a transformer can also be constructed with no physical core or a core that has no magnetic properties. Okay, a chunk of driftwood would work as a core. We could wrap our winding, our coil of wire around it, and we could build our own little transformer. Okay, again, as I've been saying, pros and cons. All right, if we don't have that highly permeable core, we're going to sacrifice considerably on the efficiency of the transformer. However, that chunk of iron adds a great deal of weight to the transformer, and if you need something light, an air core will accomplish that for you. Okay, so what are your needs? Okay, but air core is definitely an option. So the air which comprises the magnetic circuit is essentially lossless. Now this is interesting. Okay, now think about losses. There's no eddy currents here, so we're not, this is the loss that's mentioned here. There's no eddy currents. All right, there's no heat being generated in that core. Something else we haven't talked about, the flip-flopping of the magnetic field causes a flip-flopping at an atomic level within that permeable core material. That generates heat. Okay, so none of that occurs with an air core. So we're gaining in terms of our losses, in terms of our efficiency, we're gaining in that respect. Okay, before I move on with the but, I see the word hysteresis there. That's what I'm talking about. Okay, the flip-flopping back and forth. It's called a hysteresis effect, and what it does is it causes a delay in the rearranging of the atoms to magnetize the core, okay, because it's constantly changing and it's constantly changing direction. All right, so with an air core, none of that's happening. But leakage is where we lose in terms of efficiency, okay, because we are not able to focus the lines of flux. We are not able to take those lines of flux being created by the primary coil and direct them to the secondary coil. They're just sort of wandering off randomly, okay, in their very symmetrical pattern, okay, in all three-dimensional areas. And some of those lines of flux just happen to be cutting across the secondary coil. Okay, so we still get the transformer effect, but we certainly suffer in terms of leakage. Okay, so the final statement there, though, says very high bandwidth. Okay, so good for radio frequency applications. So again, we're talking about as you increase the frequency, okay, the changing of direction, so the flip-flopping of the magnetic field and the changing of the direction of the current. So back to that word hysteresis, not a problem in an air core. So an air core is probably the way we want to go in extremely high frequency applications. Okay, for our typical power distribution at 60 hertz, air core is probably not the right choice, and it really never is. Okay, so that is the core material. That is what helps us focus our lines of flux. Okay, now let's change the conversation to the windings themselves. Okay, so the piece of wire that we use to create the coils. Okay, transformer windings are conductors which are wound around the core material. Okay, so the individual turns are electrically insulated from each other to prevent a short circuit. So here's a really important point. When you look at a transformer, oftentimes the insulation on the transformer windings is a clear silicone, and it's very thin and you almost can't see it. And it looks like just bare copper wire. Well, it can't be, because then you would simply have a short circuit, and the power would come in. If you follow the current would come in and it'd short circuit across all of those wires that are touching and exit the other end of the coil of wire. So it's absolutely necessary that there is insulation there, no short circuits, so the current must travel through the entire coil, okay, because it's that coil that is what gives us our inductance, okay? So even though it doesn't look like it's insulated very often, it absolutely must be. So there's what I'm talking about. At first glance, that just looks like bare copper, okay? But the reason it's shining is because it's got this acrylic insulation that absolutely ensures there are no short circuits. Okay, for small power and signal transformers in which currents are low and voltages are small, the coils are often wound from enameled magnet wire or varnish. I'm not sure I understand that entirely. Sorry, guys. It is the varnish that is the insulation between each of those copper conductors. I think I need to reword that slide. Larger power transformers operating at much higher voltages, they may be wound with rectangular conductors insulated by oil-pregnated paper, and blocks of press board. So it's a considerably more complicated arrangement. Okay, we've got to make sure at high voltages that we can't defeat the insulation. What that means is that if the voltage is high enough, it could potentially push the current through our insulating material. Okay, that's what a spark is when you have two pieces of wire and you hold them just a short distance apart. Air is a very good insulator. Okay, but at some point there's going to be enough voltage to push the current across that air barrier, and that's what we see as a spark. So the same thing is true for any insulation. If the voltage is high enough, it can defeat the insulation and push the current through it. So in our high voltage transformers, we have to work a lot harder to make sure that we have that insulation value. Okay. Conductors are often wound so the corresponding primary and secondary windings are closely coupled to permit the highest efficiency. So this is another advantage of the shell type over the core type, is getting those two coils in essentially the same space. We get them nice and close together, and this improves our efficiency. Okay. Additionally, conductors are often wound with low voltage windings placed close to the core, while the high voltage windings are placed on top of the low voltage windings to prevent arc over. So this is something I haven't talked about yet, okay? But in order to change, this is coming in part 3, in order to change the voltage, these two coils must be different. Okay, if the two coils are identical, okay, then we call this an isolation transformer, and it doesn't change the voltage and the current. It stays the very same. Okay, it's called a 1-to-1 transformer, and the voltage in is the voltage out. Okay, if the two coils are the same. For most transformers, however, we do want to change the voltage, and so one coil must be different than the other. And we'll get to the details, but what it means is there are fewer windings. The number of turns in the coil determines the voltage of the coil, one compared to the other. So we can label our two windings, the high voltage winding and the low voltage winding. Okay, we started out by calling them primary and secondary, but that is based on not the way the transformer is constructed, but the way it is connected. Okay, the way it is constructed gives us a high voltage and a low voltage. Okay, so no matter which is the primary and which is the secondary, you're going to have a lower voltage on the low voltage coil. We'll get to all these numbers later, I promise. For now, notice that we place the low voltage coil on the inside and we wrap the high voltage coil around that. Okay, so let me get my marker right here. So here is the low voltage coil wrapped around the core, and then here is the high voltage coil wrapped around the low voltage coil. Okay, and we have three of them in this picture because this is a three-phase transformer, which I promised we will talk about later. Okay, so high voltage and low voltage, something we haven't gotten to, but I guess now is time to have that conversation, is based on the construction of the transformer. Labeling those high voltage and low voltage coils as the primary and the secondary coil depends on how we hook it up, and more to come on that in a bit. Both the primary and the secondary windings on power transformers must have external connections. They are called taps. They may have multiple external connections, which we call taps. So these are connected to intermediate points on the winding to allow for a selection of various voltage ratios. Okay, so we can see here, this is the primary side, so it's going to be connected to the AC power supply. And if that AC power supply is 480 volts, then that will be the voltage in the primary coil. If we connect, and you can't see the bottom of this because I'm in the way, okay, but just like there's a zero tap here, it's matched with a zero tap over here. So if we connect the secondary circuit to the zero tap and to the 35 volt tap, then that is our output, 35 volts. If, on the other hand, we don't connect there, we connect up here instead, then our output on our secondary voltage is going to be 40 volts. Okay, so I told you, and we'll get to more numbers later, but I told you that the number of coils, so these all represent turns of the coil, more turns in the coil means more voltage. So by adding more turns, we end up with more voltage output as a result. Okay, so we call this a multi-tap transformer, and we can have these multi-taps on one side or the other or both. Okay, and I'll give you an example of where a multi-tap transformer is really useful. I've spent a lot of time, I don't do it anymore, but I spent 15 years doing street lighting. And street lighting, every single light has what's called a ballast in it, and a ballast is just a different name for a transformer because at the end of the day it's the same thing, it's a transformer. Okay, but by using a multi-tap ballast, we can connect the same light to an environment that's at 120 volts or 240 volts or 347 volts or 600 volts. We can take that very same light and connect it to any one of those voltage environments because of the multi-tap on that ballast or that transformer. Okay, and those taps are not on the secondary side like the one we're looking at, they're on the primary side. Okay, so that we connect the primary side to the appropriate voltage, the appropriate tap, and the output on the secondary side is always exactly the same. Okay, so the multi-tap transformer makes it versatile so that we can use it in all kinds of different environments. Some transformers have their windings protected by epoxy, so this process is called potting. This is typically done in very small transformers. Okay, you see this one, it says that it's rated at 9 volts for 1.5 volt amps. There's a term we haven't talked about yet. Oh, that's a really good conversation. More to come on that later. But this is a nitty bitty little transformer. This is kind of not typical for most transformers that we're going to be talking about or working with. This is more at an electronics level than electrical work. By impregnating the transformer with epoxy under a vacuum, air spaces can be removed from within the windings, thus sealing the windings and helping to prevent the possible formation of a corona and the absorption of dirt or water. Formation of a corona, I'm not sure what that means, but we are talking about deformities in the transformer. We are talking about lack of efficiency, possibly a lack of functionality. Okay, so this produces transformers that are better for specific locations, damp or dirty environments. Okay, so we can protect the windings inside this epoxy, and then we can put this in all kinds of unsavory environments. Okay, but obviously it's going to increase the manufacturing cost. So once again, weighing the cost with the needs of the transformer. So here's a nice picture. Anybody know what this is? This is an infrared shot. Okay, something that I've done a bit of in terms of evaluating an electrical installation and determining where or if any maintenance work is required. You will go in with an infrared camera and you will look for hot spots. Okay, and where there is excessive heat being generated, you have the potential for problems, and so you want to address this. So what we're looking at here is a transformer, and as I indicated, the byproduct of a transformer, its primary waste and inefficiency is in the generation of heat, and this image shows us that this transformer is quite hot. So transformers are constructed with copper windings and steel cores, and so heat will occur due to resistance and the magnetic effects. As the power requirements for the transformer rise, so does the amount of energy lost due to heat. To prevent damage to the transformer, some form of cooling must be employed. Wow, that was a mouthful. Sorry about that. So most transformers, the small ones, there's nothing extra offered in terms of cooling. It's kind of on its own. But as you increase the voltage and especially the current, okay, you're generating more heat, and you need to take active steps to do something with that. So first of all, you have just simply air-cooled transformers. So typically these are small, low-power transformers, and we just use air to cool them. There may be no purposefully built-in cooling system, or they might have cooling slots through the core or radiator fins. So a radiator fin is simply a surface that does this. So in the least amount of physical space possible, you provide the absolute maximum amount of surface area where that heat can be released into the air or dissipated. Okay, so that's what a radiator does for us. Okay, that's what the radiator fins accomplish, is it allows that heat to get to a surface and then bleed off into the air. Okay, and it might just happen naturally, or you might even want to place a fan in there to blow air through those radiator fins to take the heat as it dissipates off the metal to get it out of there so that more heat can be released. Okay, so again, that's part of an active cooling system as opposed to just a passive one. For the larger transformers, we need more than just air to get that heat out of there, and so they are oil cooled. So high-powered utility transformers, they need more active cooling, and this is done by pumping oil through Okay, transformers are constructed with a metal housing, and the housing is filled with electrically insulated mineral oil. So here's the thing, the coil of wire is actually submerged in this mineral oil. Okay. So we can see that we have a tank, okay, and there are the windings right there, and the windings are actually submerged in the tank of oil, and the pump is moving that oil from the tank to the radiator fins where it can release the heat, and we have a fan blowing up through the fins to get that heat out of there. Okay, so a very active cooling system, not unlike the cooling system in your car's engine. Okay, the oil. Oh, I just noticed that there's an arrow there, so I guess the pump is going that way. Okay, the oil enters the chamber, the tank where the heat is, and it heats up, and then it gets pushed over to the radiator side where the fan blows through the fins to get rid of the heat, and the cooler oil is then reintroduced to the tank, and the cycle goes again and again. Okay, so actively trying to do something with that heat and get it away from the windings. Now, the oil in these transformers has to be very carefully monitored, okay, because it must be dielectric, all right? Because the coil is submerged in this oil, we don't want that oil to be conductive, all right? So when you're doing regular maintenance of your transformer substation, and I was involved in this for years, on a regular basis, typically once a year, the substation would be shut down, and we would go in and we would clean every surface. All the dust has to go, because dust typically, depending on, of course, the makeup of the dust, but dust is probably conductive, and you put dust on the wires at the insulators, and it reduces the insulation value of the insulator, and so all the dust has to be removed. All kinds of different cleaning was required, and testing was done, and one of the things that was always done was to take a sample of the oil. Okay, and so the oil goes away for testing to determine its dielectric strength. All right, and if it's found to be degrading, then you might have to add to next year's maintenance schedule the replacement of that oil. And so part of the annual maintenance would be to actually drain the oil out of the transformer and replace it with new clean oil. Okay, so that's the second paragraph there. Periodic testing of the in-service transformer oil is highly recommended to watch out for any contaminations. Okay, and as that oil ages and gets contaminated, it loses its dielectric value. So transformers, here's a transformer label. Okay, so we've got all kinds of information here. What's highlighted though is the type of cooling, and there will be 4 letters that will identify how that transformer is cooled. Okay, so let's move on to the next slide, and we'll find out what these 4 letters represent. Okay, so the first 2 letters talk about what's happening internal to the transformer. Okay, so the first letter is what is the medium, okay, and typically is it air or is it oil? And then the second letter is what is the mechanism? Is it passive or active? Okay, there are other various levels to this, which we'll see in the next slide, but this is basically the idea. And then external to the transformer, what is the medium and what is the mechanism? So again, is it still just air or is it oil? And the mechanism, is it passive? Is it just a radiator fin, or is it active? Is there air being blown across those fins to move the heat? So medium and mechanism, both internally for the first 2 letters and externally for the third and fourth letters. And so this is not test material. I'm not going to be giving you a 4-letter cooling classification and ask you to tell me what it means, but you must understand what's happening here. So we can see, and because I'm not going to go through all of these letters, but the first letter is the cooling medium, okay, O for oil, L for liquid, and they are different based on their flash points. Okay, how hot can this stuff get before you start to get nervous about, flashover, something burning up. Okay, second letter, cooling mechanism. N is for natural, F is for forced, D is also for forced. Okay, different version of construction. And then externally, we have air and water, or we have natural convection or forced circulation, which is going to be your fan. Okay, so cooling of a transformer is a really big deal because primarily that's what it does. It's not going to break because of moving parts. Okay, it's going to break because it overheats and the insulation around the coil gets compromised. Okay, so heating is the issue, so cooling is important. So we're back here. Notice that the type of cooling was ONAN. Okay, so internally greater than 300 degrees Celsius, liquid cooled. Okay, so we've got a liquid coolant system inside with natural convection, which means there's no fan here circulating the oil from inside to outside. It's using the natural flow that's going to happen as this liquid heats up and cools down. Okay, and then A means external air cooled, and N means natural convection. So again, there's no fan forcing this. It's just utilizing the construction of the radiator. So that's what those four letters mean. Okay, so like I say, that's not really test material. I'm not going to ask you to memorize that previous table. Okay, but conceptually you must understand what these four letters represent, and every transformer has those four letters indicating the mechanism of cooling that's being used. Okay, transformer terminal. So how do we actually connect to this transformer? Okay, and for all small transformers, they're just going to be wire leads. Small transformers have wire leads. We just marret our wires onto it, and we've made our connections. Nice and straightforward, nothing terribly difficult. As we move up a little bit in terms of size, a slightly larger transformer will have screw terminals. So now we're putting the wires, probably using a fork stake-on or something of that variety, to connect to the terminals which are provided with the transformer. And finally, when we get to the much larger transformers, we are going to be connecting to them using these bushings. So these are large insulated polymer or porcelain bushings that hold the wires apart. So remember, I've talked a couple of times about the fact that if you have enough voltage, it has the ability to push the current across an air gap. So these are very high voltage transformers, and so the bushings ensure that the wires are held far enough apart that the voltage can't push the current across those air gaps. Keep those air gaps extremely large and you won't have that problem. Okay, so that's the purpose of the bushings. They also provide separation from the wire and the transformer itself. So remember, the transformer, you can see it there, is made of steel. Okay, it's all grounded. Okay, so you certainly don't want the wire to actually arc to the transformer housing itself. So the bushings offer that protection also. Okay, they're very large insulators. They keep everything well separated so that there's no potential for arcing. So that concludes part one of this slideshow. You'll see, if you've printed this off and following along, you can see there's more to come. And so I will come back with part two. But that concludes part one of the lesson.